Okay, welcome to the network seminar. And our speaker today is Marco Nurisso, and he will talk about interactions and topological synchronization in the Simplicial Kuramoto model. Go ahead, Marco.
Okay, thank you very much. Thank you for the invitation. I'm very happy to be here and give you this seminar. And okay, I'm gonna talk a bit about this work that I did for the first part of my PhD, and it is about simplicial complexes, about dynamical systems on simplicial complexes, and a very specific one, which is the Simplicial Kuramoto model. And I will explain you what it is and how it is built and what we did on it. So, very brief plan of the talk. I'm going to start by giving you a brief motivation of what is the setting in which this work is embedded. So dynamics in complex networks and higher order systems in general. And specifically, I'm going to give you a brief primer on a synchronization phenomenon and the Kuramoto model, which is used to describe this. And then I'm going to get into the heart of the matter, which is the Simplicial Kuramoto model, how it is built using discrete topology tools, and then some of interpretations of its phenomenology and results that we can get on it. So let me start. This is a network seminar, so I don't think I need to give you a lot of motivation for this, but complex networks are everywhere in all kinds of systems. We describe networks with graphs, so nodes and edges, and often we are interested in doing something with this graph. And with something, I mean putting something on top of the structure, usually a dynamical system, which can tell us how some state of the system as a whole evolves in time. For example, we have models for opinion dynamics on networks, for synchronization, for like infection, spreading, and so on. And in recent years, there have been a great amount of interest in something which is called higher order systems. And this stems from the observation that networks have a problem, or more like a limitation, that is that networks are made of nodes and edges can only connect two nodes at a time. And this is what it's called a pairwise interaction. If you want to describe a system of interacting things, where these things, these agents are the nodes, if you use a network, you can only describe interactions where two of these nodes interact at the same time. But there are multiple systems, real-world systems, where this is an approximation at best, and where group interactions, so interactions which involve more than two nodes at a time, are actually relevant. Think, for example, of social systems, like a group of people being friends, where the interaction, the friendship, which ties together a group of friends is much different, is very different from a set of pairwise friendships between its members. And this also appears, this kind of group interactions appear in biological systems, in brain dynamics, and so on. And so a lot of people did a lot of work to try to formalize this and extend the network formalism and the dynamical systems on networks onto higher order networks, so systems which can support group interactions. And we do this usually using hypergraphs and simplicial complexes. So basically, hypergraphs in general are just networks where you take nodes, edges, and you add other higher order structures, such as triangles, tetrahedra, and so on. And in hypergraphs specifically, you don't have any restriction on these particular higher order interactions. And so this makes hypergraphs a very flexible tool to describe in a realistic way systems, higher order systems. But sometimes you can also be content with an extra assumption, which is the downward closure properties, which assumes that every subset of an hyperedge, which is an edge, a generalized edge, is still an hyperedge. And if you do this assumption, you get a simplicial complex. And while simplicial complexes are more limited because of this restriction, this assumption, you can actually use a lot of tools which comes from combinatorial topology. Hence, we are here. So, given this formalization and this interest in higher order systems, a lot of different network dynamics have been extended to simplicial complexes, starting from social contagion, random walk, and even synchronization, which is the main topic of this seminar. And turns out that you can do these kind of extensions from network to higher order networks in many different ways, depending on the assumptions you make on the structure and so on. And just for synchronization, there are different solutions which can lift the synchronization dynamics from networks to hypergraphs or simplicial complexes. And in this talk, I'm going to focus on one particular one of these solutions, which is the one by Millan, Torres, and Bianconi from 2020. But first, I'm going to tell you a little bit about synchronization. And synchronization is simply described, I think, it is a phenomenon which you find in nature, which can be, I think, simply described by this GIF. You have a set of things, set of oscillators, which have a state which oscillates. They each have a frequency at which they tend to oscillate when they are left alone, and they are then put in interaction. They communicate with one another in some way, and through this interaction, this communication, they actually achieve a synchronization of their rhythm, an autonomous, a spontaneous synchronization of their rhythm, like you see with these metronomes on this wooden table. And the most famous, no, before that, you find this synchronization phenomenon in many systems, real-world systems, ranging from audiences which applaud. You find that in some situations, people will start clapping at the same time because of the waves transmitted by the seats of the people. But you also find it in the blinking of some species of fireflies, but also in more practical scenarios like the synchronization of power grids, which is an engineering problem. And the most famous model for describing synchronization is the Kuramoto model, which was devised in the 70s. And it has had a lot of success in these years because it is a very simple model and actually is able to describe with a very simple mathematical formalism this synchronization phenomenon. So very briefly, how does it work? You consider a set of n oscillators and you assume that they are phase oscillators. And this means that you can describe each of their state only by a single number or a position on the circle, which you call a phase, which is basically an angle. Each oscillator has a natural frequency, which is a real number, omega, and the natural frequency of oscillator I is the frequency at which oscillator I will tend to oscillate when it is left alone with no interactions. And then these oscillators are coupled with a given strength, which is a real number, a real positive number. And the coupling is given by this particular coupling function, which is the sign of the difference of phases of oscillators. And if you build this model and simulate it, you actually find that you get what you expect. You are describing a synchronization dynamics, where you see that you start with points, so phases, which are all scattered around the circle and they move at different speeds. But after just a while, they start, you see, converging, collapsing, and actually synchronizing, so moving at the same speed with the same phase. And the original Kuramoto model assumes an all-to-all coupling, so you can think of it as happening on a complete graph. So every oscillator interacts with all the other oscillators. But it is fairly easy to extend this to a network dynamics simply by taking a graph, its adjacency matrix A, and plugging it into the dynamics, the coupling function, in such a way as to, like, what this means is that each oscillator will only feel the state, will only interact with the oscillators which are in its neighborhood. And if you simulate these dynamics on a graph, like in this example on the right, you see that under some conditions, you get mostly the same behavior. I mean, you start from oscillators with different phases and different speeds, different frequencies, and you get on spontaneous, if the graph is connected and so on, spontaneous synchronization of their frequency.
And the graph here is the graph of the neighbors.
Yeah,
Okay.
exactly. Okay. So to give you a taste of what will come later, I put here a slide which I call topological formulation of the Kuramoto model, which is probably an overstatement, but what I want to show you is that you can actually use some very trivial tools and definitions from combinatorial topology to describe this model in a very compact and elegant way. So the idea is that you start from your graph and you assign arbitrary orientations to the edges of the graph. And so what you get is an oriented simplicial complex. I mean, it is a very trivial simplicial complex because it has no triangles or higher order simplices, but it is nonetheless a simplicial complex. And given a simplicial complex, we have algebraic machinery on top of it. In particular, you can define cochain spaces on a graph, just the 0 cochain space and the 1 cochain space, which are just real functions respectively on the nodes and on the edges. And from this, it is easy to see that the phase configuration, which is an assignment of a phase to each node, can be described with a 0 cochain. And relating these two cochain spaces, we have the coboundary operator, which can be represented by a matrix, which I call D0. And turns out that if you use this matrix and its adjoint, which I call B1, you can rewrite the Kuramoto model on a graph in a very compact form, which is this one. What we get is that theta now is a vector, is a 0 cochain, and its derivative is given by the natural frequencies and the coupling term, which you see is a very simple form and is telling you that you start with theta in the 0 cochain space, you map it onto the 1 cochains with the coboundary, you apply an element-wise nonlinearity, which is the sign here, and then you go back. And this formulation is, apart from being like elegant and beautiful, is also useful because you can use it to prove different things. And a very simple thing that you can prove and you can see with this formulation is the following. For example, assume that the graph is connected and we have no natural frequencies, so this is 0. What you get is that a sufficient condition to have equilibrium, so no, the theta dot equals to 0, so that the system stops, is for theta to be a 0 cocycle, because so an element in the kernel of the coboundary, the 0 coboundary. And given that we are on a graph and there are no 0 coboundaries, this means that theta must be a representative of the 0th homology class. And on a connected graph, homology classes correspond to functions which are constant on the nodes. And so what did we find? We found that basically that the synchronized solution, where all the oscillators have the same phase, is actually an equilibrium of the system. Of course, this is very simple and trivial, but it is meant to be a proof of concept of this approach.
Is it difficult to prove that this doesn't depend on the chosen orientation of the graph, or is it like a trivial thing?
Yeah, it's actually not that hard because I will get to that later, but you see that this term B1 sine of D0, if you linearize it, you can remove the sign and you get D0 B1, which is just the graph Laplacian, and the graph Laplacian on the nodes is independent on the orientation on the edges. So right. You get it from there.
Right.
Okay. So let's get into the more interesting stuff. As I told you before, in 2020, this paper came out by Millan, Torres, and Bianconi, which gave one possible way to extend this Kuramoto model to simplicial complexes, so to higher order networks. And this, I think, is very interesting because it is distinguished from other kinds of generalizations because it allows you to change the meaning of the oscillators and to pass from a situation where the oscillators are the nodes and they interact through the edges to a more general one where the oscillators are the k simplices and they will interact through k+1 and k-1 simplices. What does this mean? Before we had a situation like this, we have a graph and we had phases on the nodes. Now, on the same graph, without going into complex simplicial complexes, you can instead define a synchronization dynamics, which happens on the edges. And now you will see that the color will be of the edges. And already from this simulation, you see that there is some phenomenology that you don't see in the node case. In the node case, we start from an heterogeneous distribution of phases and we get to synchronization. So all of the nodes oscillating at the same speed. While here, we already see from this brief look something different. We see some oscillators which freeze after some time, others which tends to oscillate, resulting in some sort of traveling waves, which seem to be localized around the cycles of the simplicial complex and don't seem to stop during the dynamics. So my goal with this work and this talk is to tell you what are these kind of phenomena that you can see and how you can actually explain some of them using math. So first of all, I want to tell you briefly how this model is built and what does it look like from the mathematical point of view. So let's take a simplicial complex, a finite simplicial complex delta, and let us fix an order k. For simplicity, let us fix k equal to 2. This means that we want to describe a synchronization dynamics where the oscillators are the two simplices, or in general the k simplices, in this case the triangles. Once again, we have cochain spaces, C0, C1 up to C3 in these examples. And given that we want to describe synchronizations of triangles, it is then only natural to consider theta as an element of the second cochain space, so a real function on the triangles. These spaces are related by co-boundary operators of different orders and their adjoints, which I call, with an abuse connotation, boundary matrices. And so the idea to extend the Kuramoto model is to play the same game as before. You take your theta, you map it up with the co-boundary, you apply element-wise sign and nonlinearity, and then you go back with the adjoint operator. And so we can build in a very straightforward way a generalization of the Kuramoto model, which is now happening on the k simplices or the triangles. And I call this a straightforward extension because it is, let me say, a one-to-one mapping, in the sense that before we had nodes, which are oscillators, which interact through one simplices, so edges. Now we have k simplices, triangles, which interact through k plus 1 simplices, tetrahedra. But the interesting thing of this model is that this is not complete, because when we work with simplices of order greater than 0, so or greater than nodes, we actually have that simplices, k simplices, can be adjacent in different ways. Two triangles, that is, can be adjacent through tetrahedra when they are faces of a common tetrahedron, but they can also be adjacent from below, so through edges, when they share a common edge. And this doesn't happen when you work with nodes, because there are no -1 simplices which can give you this adjacency from below of nodes. So it is very natural to do the same thing, but backwards, and take theta, map it down with the second order boundary matrix, apply the sign, and go back. And so what we get is this threefold model, which has 3 terms and 2 interaction terms. One,
a very simple question before you go back.
Sure.
Because this is my opportunity, I think, to understand this Kuramoto model.
Yeah.
So in the one-dimensional case, I can think of an oscillator as just a function on a node or a function on something, and then I have a set of functions on a node. So how should I think of an oscillator of 2 chains? Because a 2-chain is like a map from a group of nodes to real numbers. So what is an oscillator here in dimension 2? What does it mean?
Well, that's actually a very good question. Mathematically, this means that we have a phase assigned to each triangle, simply. That it. Imagine each triangle, it is an oscillator, so it has a phase, it is oscillating. The physical meaning of it is another question, which is non-trivial, and I don't think there is a straightforward way to interpret this physically.
Okay, thanks.
Yeah.
So maybe I also want to ask about this, because I wondered many times. So you've never come across like any actual example where there is a simplex in some real world setting that is oscillating like that? What would it mean?
Well, yeah, I mean, that's a good question. I mean, I thought of it for a long time. I'm still thinking about it. I think the most natural examples would be for oscillators on edges. So where you have like flows inside a network which are oscillating. This, I think, could be something which can have some practical and physical interpretation. But in general, I don't see one at the moment, although I'm looking for one.
Okay, all right. Another question is just to check. So sigma here, that's some kind of coupling strength between simplices?
Yeah, exactly. It's just a real number, which is the higher it is, the higher is the coupling, the stronger is the coupling.
Okay, so it's just arbitrary choice, or do you have some study somehow that comes up somewhere naturally, like on the simplicial structure or something? Or
well, in principle, you can have it to be any number, and if you tune it, we will see that you will get different things, different behaviors. But what is the relation between the value of sigma and the behavior of the model, I'll tell you a bit later.
Okay, cool.
So there is an interaction, a connection between these two things.
All right, cool.
Okay, so if there are no more questions, I go on. As I was saying, we get this model with 3 interaction terms, which is very elegant and compactly written. As I told you, we have an interaction from above, so k simplices through k plus 1 simplices, and an interaction from below, k simplices through k minus 1 simplices. This is a generalization of the standard Kuramoto model, trivially, because if you take k equal to 0, then there is no interaction from below, so you get exactly the standard Kuramoto model on a graph. And another interesting thing that you can observe is that, as I told you before, in the standard Kuramoto case, you can linearize this model around the 0 solution. If you do this, the sign disappears, and what you get is that this dynamics is actually a nonlinear extension of a combinatorial Laplacian dynamics. So a dynamics which is where the interaction term is linear and is based on exactly the combinatorial Hodge Laplacian of order k. And we will see how the nonlinear dynamics actually is rooted on this Hodge Laplacian dynamics, and some of its properties actually comes from these. So then, as I told you before, the approach is this. We have the model, we can simulate it, we can look at it, we see some different behaviors, and the goal is to actually understand what's going on mathematically for some of these behaviors. So first thing that we can observe, to answer to your question before, what you see is that if you increase the coupling constant, the coupling strength sigma, then what you see is that the system actually is getting closer and closer to some sort of equilibrium. What it means is that if sigma is high enough, what you get is that you start your dynamics, it goes on until it gets to a stable state. You see, in this extreme case, the width of the edges is the frequency of the oscillators. What you get is that, for example, some of these oscillators freeze, they stop moving, while others keep moving at constant speed. And in particular, we see this localized around the cycles of the graph. Where does this come from? Well, you can explain this using the well-known combinatorial Hodge decomposition theorem. This is a theorem which tells you that any k cochain space, which remember is the space of phases of our oscillators, can be decomposed into 3 orthogonal subspaces. One is the image of the coboundary, one is the image of its adjoint, so the boundary, and the third one is the kernel of the Hodge Laplacian, which is called the space of harmonic cochain. And this means that every k cochain can be written in a unique way as the sum of 3 orthogonal components, which we name curl-free, harmonic, and divergence-free. And this nomenclature, this kind of names that you give to these components comes from the continuous case, because you can define the Hodge Laplacian and the Hodge decomposition even for differentiable manifolds. And if you look at vector fields, this decomposition is more well known as the Helmholtz decomposition. And it is telling you that you can take any vector field on a manifold and write it as the sum of a divergence-free vector field, so a vector field which you see as no sources nor sinks, a curl-free component which has no circulation and only like only sources and sinks, and then an harmonic component. And the harmonic component, you see, kind of wraps around and is localized around the holes, the k-dimensional cavities of the simplicial complex. And this comes from the fact that the kernel of the Hodge Laplacian is actually isomorphic to the kth homology group of the simplicial complex, or the kth, the RAM cohomology group of in the case of manifolds. So what do we do with this? We have a dynamical system which is based on a k cochains. You can apply this theorem to the phases. So you can write each phase, each configuration of phase and the natural frequencies cochain as sums of 3 independent and orthogonal terms, the curl-free, harmonic, and divergence-free. And what you can do is then write dynamics, so the differential equation, which is telling you how each of these components is evolving. And what you find, strikingly, is that each of these equations is independent from the others. And this means that, for example, you can write the equation, which is telling you the evolution of the curve-free component as, a differential equation, which depends only on the curve-free component and doesn't depend on the harmonic and the divergence-free one. So effectively, when we work, this means that when we work with the Simplicial Kuramoto, we're actually working with three models, three different dynamics, which are operating independently at the same time. And what you see is just their sum. And so it is very natural to, instead of working with the full model, which is more complex, to work on the, the split model. So each of these decoupled equations separately. And an interesting thing that you can see by looking at this is that the harmonic component, so the second one, is not at all affected by the interactions. This, in fact, it evolves according to a very simple differential equation, which is telling you that the frequency, the harmonic frequency of the dynamics is only equal to the harmonic part of the natural frequencies. So these subdynamics of the model always moves at constant speed, and it is not at all affected by the interactions or the coupling strengths and so on. And given that it is harmonic, we can think of it, we can see it being localized around the k-dimensional holes. And this is kind of explaining something of the behavior of the model that we see here. It's explaining the fact that we see this circulation, which is constant at constant speed, as these waves move at constant speed, around exactly the k-dimensional holes, so the cycles of the graph in this case. Going on, given a dynamical system, so it is very natural to then ask what are the equilibria of the model, what are the fixed points, so the configuration of phases which are left unchanged by the dynamics. And once again, we can leverage the Hodge decomposition to split down the problem in three and ask about conditions for equilibrium for each of the three components. And just a technicality, it is actually not very easy to work with the curve-free and divergence-free components separately, because this would amount to actually considering projections into subspaces of the Cauchy space. And when you talk about equilibria, turns out that you can prove a simple proposition, which is telling you that you can equivalently work with other quantities, which are theta minus and theta plus, which are basically projections of the phases on k minus 1 or k plus 1 simplices. So theta minus is like the boundary of the phases, so the projection through the boundary matrix on the nodes, so the k minus 1 simplices, while theta plus on the k plus 1 simplices. Think of, in the case of edges, on the triangles. And we get that curve-free component is in equilibrium if and only if theta minus is in equilibrium, and the same for the plus component. So what we can study these equations, but first of all, we can ask, what do they mean? What does it mean to have, for example, a curve-free component which is in equilibrium? Well, we can see very simply that a curve-free component in equilibrium is akin to a flow conservation condition. What does it mean? You can write down theta dot, so the derivative of theta minus in time is equal to 0. You're asking for the fixed point. And by applying the linearity of the derivative, you can see that this is equivalent to saying that the frequency, so theta dot, the derivative of the phases in each simplex, is a cycle, a k-dimensional cycle. This means that, as I told you, is a flow conservation condition, in the sense that at every k minus 1 simplex, all the frequency coming in needs to go out. And you can see it very well when you have k equals to 1, so phases on the edges. All the frequency coming into a node needs to go out. And you can use this interpretation to find some and explain some behavior of the model. For example, you can prove from this that oscillators with free phases must be frozen. And this explains why this branch of the complex actually dies out in the oscillation after some time, because it has a free phase, so a node which only belongs to one edge. And also you find trivially that manifold regions are frequency synchronized. And with manifold regions, I mean regions of the simplicial complexes, of the simplicial complex, where, at least in the case of edges, each node belongs to exactly 2 edges. And this is why you see this oscillation. specifically these waves around the holes, which are at constant speed. That's because the oscillators are frequency synchronized. They move at the same speed. So this is another thing which we can somehow explain using this interpretation. And getting a little bit more technical, it turns out that you can actually find conditions for this equilibrium to occur depending on the value of the coupling strength. So in particular, you can prove a necessary condition for equilibrium. So you find that for the system to be in equilibrium, you need sigma, the coupling strength, to be greater than this sigma star coupling, which can be easily computed as the solution of an optimization, a linear optimization problem, which you see is ranging over the space of k+1 cycles. And from this, what you see is that, for example, if the simplicial complex is acyclic in the order k+1, so there are no k+1 cycles, then this optimization space is empty. And what you have is that you can actually compute very easily the value of sigma star as the infinity norm of one particular vector, which I will explain you in a bit. But more importantly, you can also find a sufficient condition. So you find that if sigma is greater than this sigma fp, which is a constant times the two norm of the same vector as before, then there exists an asymptotically stable equilibrium. What does this mean? It means that you know that if you tune this sigma high enough, you can actually get to equilibrium, or at least an equilibrium which is stable exists. And interestingly, these two norms can be related to the effective resistance of the natural frequencies in the simplicial complex. Of course, effective resistance, which is a quantity which is defined for graphs, extended to simplicial complexes. And so I think this results in an interesting interpretation, because this beta plus vector, that is the norm of this beta plus vector, is in somehow encoding the structural resistance of the network of the simplicial complex to synchronization. And it depends both on the structure, so the adjacencies of the different simplices, but also the natural frequencies. So all the structural parameters are here. And if the coupling is able to go beyond, to go further, to be larger than this resistance, then you can actually achieve synchronization. And just to conclude, another thing I would like to talk about is that related also to the question of physical interpretability of this model, is that what I call peculiarity of the simplicial model. The thing is that when you work with these kind of systems, which are based on the Hodge Laplacian, you find that it is hard to interpret what's going on, the physical meaning of the system. And this comes from different behaviors that are encoded in this kind of interactions, which you may not expect when you start working with this kind of system, but are here. For example, what you see is that, at least for the case of phases or oscillators on the edges, that interactions which occur at nodes which are manifold-like, so they belong to exactly two edges, are exactly the same as standard Kuramoto interactions, because you see that the term that you will get in your equation is, if you remember, the equation I showed you at the beginning is just the difference of the phases of the two edges. But at the points which are non-manifold-like is where the model starts becoming interesting. For example, if you have three edges which are all incident on a node, this node will result in an effective higher order interaction. So an interaction which is non-linear in the three phases of the oscillators. But also at boundary nodes, so nodes which are, so edges which have three phases, you find that these nodes still account for interactions which you can think of as self-interactions. Is the edge interacting with itself in such a way as to stop its oscillation. So what I want to say is that these peculiarities are like inherent to the way you can formalize these simplicial models. And so if you want to work with simplicial models using these Hodge Laplacian boundary matrices and higher order cochains, you need to be aware of these facts. And trivially, from this observation, this interpretation, you can see that even in the simulations, we see that in the manifold-like branches, so the branches of the graph where you have two edges connected to every node, the behavior is kind of simple and trivial, like you have these simple synchronization dynamics, while the non-trivial behavior, which is inherent of this simplification model, comes exactly at these circle points, which are the non-manifold points, so the crossroads and the free phase. And from this, you can also prove, I mean, very easily, that on simplicial manifolds, so like spaces where k-1 simplices are adjacent to exactly, are contained in exactly two k-simplices, then the model, the simplicial Kuramoto model, is exactly the same as the standard Kuramoto model. And this follows from Poincare duality. You can just put a node on each of the k-simplices and build a graph, and you will find that the dynamics is actually equivalent.
On the maximal simplices, or
exactly in the maximal simplices.
But in the lower dimensions, in the middle dimensions, there could be something else happening.
Exactly, yeah. You don't have that. For the dynamics to be equivalent to the standard Kuramoto, so the k-dimensional dynamics to be equivalent, you want the complex to be a k-dimensional manifold. Otherwise, it doesn't hold. And so, yeah, so to conclude, just want to say that using some tools of combinatorial topology, you can study these kind of models. You can actually prove, study the equilibriums, the synchronized configuration, give some interpretation of them regarding them being localized around the holes and the harmonic cochains. You can prove necessary and sufficient conditions for them to exist. And also the idea is, the message I want to pass is that the last thing I talked about is that when you work with these simplicial systems, in this way, with this formalism, you need to be aware of these peculiarities, these interactions, what these interactions will do at what I call non-manifold points. So I want to thank you for the attention and for inviting me. If you're interested, we have a paper out describing these. And of course, I'm open to questions.
Okay, thanks, Marco, for the great talk. So let's unmute to give Zoom applause. And any questions for Marco?
I have a question if people are not daring. Could you tell me what this, like you told us the interaction is kind of, how does it look when they interact one dimension lower? How does it look, just for me to understand a bit better, when they interact from above?
You mean, how does it look in the, in the actual equation?
Yeah.
Yeah, I'll tell you, I show you. Well, what you get is that it depends on the order. So for example, if you have
we can do edges to two simplices too.
Yeah, for example, edges to triangles,
yes.
You will get this kind of term. So you will get an ordinary interaction because you have three edges which are projected onto a single triangle and will be summed in this triangle, and then you will apply the sign. So you will get this kind of higher order interaction, which will always involve k+1 phases.
Yes, that's the boundary. Okay.
Yeah, exactly.
So you said that you get this sort of peculiar dynamic. So is it more like what does it mean? Like, is there a more precise definition, or is it just like in the simulation in the neighborhood of this crossroads? It's not synchronized. It's not anything. It's just, flashing in a random way.
Well,
is that what you mean, or?
Yeah, what I mean, of course, I know it's not a really precise term. What I mean is that when you work, I mean, it is different from the standard Kuramoto. So it is different from a dynamics in which you have phases, and these phases tend to get closer to each other and synchronize. When you have these kind of interactions, so these non-manifold points, you don't have that. The phases are not necessarily trying to get closer to one another. Of course, the model is still trying overall to get to an harmonic cochain somehow, so being localized and oscillate around the holes, but this doesn't mean that you will get to a synchronization in the standard sense.
Right. We have a question in the chat. would it make sense to have a different sigmas for the interactions from above and interactions from below?
Yeah, this is a good question. Yes, you can do it. We do it in the paper, and given that you can use object decomposition to decompose the dynamics, you can think of tuning the coupling from above and from below separately to get, you can get, for example, equilibrium in one and not equilibrium in the other, not equilibrium in the first, vice versa, or equilibrium in both independently. So yeah.
Okay, do we have any more questions for Marco?
I have one last one and then I stop because I think I'm hogging. Can you go to the decomposition of the dynamics in the harmonic and non-harmonic parts?
Yeah, I would like to change slide without closing everything.
With the mouse, maybe? No,
Okay.
sorry, with the, yes, arrows. Yeah, anyhow, that's fine.
Why? It's not working. Okay.
No, not
Oh,
that
the
one.
dynamics
No,
you
not that
meant.
one. Like really that one. Yes.
Okay. Sorry.
Thank you. So here this WH is fixed for the entire complex. This omega H, sorry, is fixed for the entire complex.
Yeah, omega is fixed a priori, is on a hyperparameter, you can say.
Uh-huh.
Yeah. So omega H is the projection to the harmonic space of this omega.
So does this mean that the homology classes that are there, like the harmonics, will tend to have the same frequency in the entire complex?
Yes, that's the
Okay.
point. And
Okay.
vice versa, if there are no k-dimensional holes, then you will see that this is zero. So there is no harmonic component. So you get only the curve free and divergence free, which if sigma is high enough will go close to zero. And so you will get the dynamic will freeze at some point. That's what you get. Yeah. So in some sense, the k-dimensional holes in this simplicial model are the ones which are responsible for keeping the dynamics active. They are the synchronized, the synchronized, the responsibles for synchronization. Yeah.
Okay, thank you.
And thank you for the question.